Yeah. So it's a pleasure to welcome Carlos Olmos from the Universidad Nacional de Córdoba, Argentina, speaking on Hopf-Berger and totally geodesic submanifolds. Thanks.
Thank you very much for the kind invitation to Caroline, Emilio, and Ramiro Lafuente. So thank you very much. I'm very honored to have been invited to this seminar. So let us. So the title is, of course, we will speak about Hopf-Berger, so totally geodesic submanifolds of Hopf-Bergers. This is a joint research with Alberto Rodriguez Vázquez from originally from the University of Santiago de Compostela, but he's now in Leuven, I think. So let us begin. So these are the topics. So let us start with the well-known fibrations introduced by Heinz Hopf in the 30s. So the well-known. So the first one is with fiber S1, then the second one is fiber S3, and the third one is the fiber S7. Of course, these are the spheres. So the first one, we would refer to the first one as the complex Hopf-Berger, then the quaternionic Hopf-Berger, and the octonionic Hopf-Berger. So diffeomorphic play a fundamental role both in geometry and topology. The base space has the Riemannian metric of maximal sectional curvature equals to 4. We put by convention this is better for the calculations. So maximal sectional curvature equal to 4, and the total space is the round sphere of curvature 1. Oh, of course, if we begin with the sphere with curvature 1, of course the other the curvature of the base is completely determined. Hopf-Bergers are Riemannian submersions and have totally geodesic fibers. So the fibers, so in the first two Hopf-Bergers, the fibers are given by the action of a group. In the octonionic case, so though every fiber is homogeneous, there is no group action that gives all the fibers at the same time. So Riemannian submersion from the round sphere. So I recall well-known result and strong result from Gromol, Grove, and Wilking. Riemannian submersion from a round sphere with connected fibers of positive dimension is metrically congruent to the Hopf-Berger. Now we will rescale the metric of the total space of the Hopf-Berger by a factor tau greater than 0, only in the direction of the fibers. So we rescale the metric in the fibers of the Hopf-Berger. So the more known, so is the complex Hopf-Berger. We just rescale the metric in the direction of the orbit of the x1 action. So these spaces are the so-called Hopf-Berger spheres of factor tau. So the Hopf-Berger spheres of factor tau, and denoted. So we denote with this notation. So the first one is the complex, the second the quaternionic, and the third is the octonionic, and the factor is tau according to the type of the Hopf-Berger. So when it is not specified the type of a Hopf-Berger sphere, it is denoted by this. So the total space. So a Hopf-Berger sphere has positive curvature if and only if, this is our calculation performed by Verdiani and Siller, the tau is less than 4/3. Moreover, any Hopf-Berger sphere with tau different from 1, of course, not the round sphere, may be regarded as a geodesic. This is very important for our purpose. So any Hopf-Berger sphere may be regarded as a geodesic sphere of a rank 1 symmetric space with non-constant sectional curvature. And conversely, any such geodesic sphere is a Hopf-Berger sphere. Of course, Hopf-Berger spheres are the usually Berger spheres when tau is less than 1, and some people call when tau is greater than 1, Berger spheres are called anti-Berger spheres. But this is the generalization of the well-known Berger spheres. So this is in order to fix notation, and then so the quotient space has these properties. So now a Berger sphere or a Hopf-Berger sphere we regard as a geodesic sphere in an appropriate symmetric space. And so the group K acts in this geodesic, on this geodesic sphere, and this is just the isometry group or the connected component of the isometry group. Because they are the transformation preserving the Hopf fibration. So a Hopf-Berger sphere is homothetic to a geodesic sphere of radius. So we will now give more precision on what we said. So the Hopf-Berger sphere is homothetic to a geodesic sphere of radius t, where tau is the factor, we rescale the fiber, and t are related by the following formula. So we have a homothetic factor because the ambient space have maximal curvature 4 or minus 4, the minimum in the non-compact case, and then because of that we need a homothetic factor. So this is it's a well-known things about this sort of spaces. So the fibers of a Hopf fibration from a Hopf-Berger sphere regarded as geodesic spheres are given by the intersection. This is very important in order to have a very good geometric understanding of such spaces. So the fibers, so in this model as geodesic spheres, are given by the intersections of the geodesic sphere with Helgason spheres of the ambient space that contain the center. So that are spheres of the maximal curvature. So in that way, so we can regard the fiber as the intersection of a Helgason sphere with the geodesic sphere. Hopf-Berger spheres are geospace. Geospace, geodesic orbit space, that any geodesic is given by the orbit of a one-parameter Lie group. Moreover, so geodesic, these Hopf-Berger spheres are naturally reductive spaces, with deception when tau is different from 1/2 in the octonionic cases are only geospaces in general. and not naturally reductive. So the purpose of this talk is to focus our attention on the geometry of Hopf-Berger spheres, and in particular on totally geodesic immersed submanifolds. So we will, at the end, we will classify totally geodesic immersed submanifolds, but a posteriori would be embedded. We will show the classification of totally geodesic submanifold of Hopf-Berger spheres. Some of them, of these totally geodesic spheres, are the standard totally geodesic submanifold of geodesic sphere. In any geodesic sphere, totally geodesic can be constructed at the intersection of a totally geodesic submanifold of the ambient space that contains the center of the sphere, of the geodesic sphere, with the geodesic sphere, as the sphere, in general, totally geodesic submanifold of the sphere, this generalizes. So in general, are intersection of linear subspaces with the standard sphere. But in this way, these are the standards totally geodesic submanifolds of geodesic spheres. Intersection with totally geodesic submanifold of the ambient space that contain the center. But surprisingly, for tau less than 1/2, except for the classical Berger spheres. In the classical Berger sphere, so when the fiber has dimension 1, the complex associated to the complex Hopf fibration, appear as some exceptional totally geodesic round spheres of dimension of the fibers. So it appears some other that are not fixed points of family of isometries, are not fixed point of families of isometries. Otherwise, it would be the intersection of a totally geodesic of the ambient space with containing the center. And so this is only to motivate, so it has nothing to do with exceptionals or holonomies or nothing to that. But so this, in some way, we construct in some way these exceptionals. So by bringing back the fibers from other points by using parallel transport in the ambient space, and then in some these exceptionals are constructed in some systematical way, but surprisingly also appear some others that cannot be carried out with these general constructions, and are totally geodesic RP2 and RP3. So it appears as, so it was surprising. So in particular, we found the totally geodesic RP2 in the 7th sphere, in the Hopf-Berger 7th sphere, quaternionic 7th sphere of tau equals to 1/3. So if we now see from Wilking's connectedness principle, one has that RP4 cannot be totally geodesic in such in a 7-dimensional manifold with positive curvature, in a 7-dimensional manifold of positive curvature that is homotopic to a sphere. But now, so the Wilking connectedness principle is a constraint. So RP4 cannot be totally geodesic in immersed or embedded. But now we construct an RP2. There was the first example of such a totally geodesic submanifold because in a manifold of positive curvature homeomorphic to the sphere. and diffeomorphic to the sphere. And then, so the natural question is if one can, if RP3 can be a totally geodesic manifold of a manifold which is diffeomorphic to a 7 sphere. So in this talk, we will mainly emphasize on many geometric general facts. O sea, so our main point here is to emphasize some geometric general facts that could be useful in a more general setting also. So that's...
Excuse me, Carlos, there was a question in the chat. Gil, would you like to ask a question?
Yeah, maybe I ask it directly, not the chat. So, hola, Carlos.
Hola.
Okay.
Gil.
Sí, soy del CIMAT.
¿Cómo estás?
We met some years ago. Okay. Sorry, I'm kind of the first non-trivial example kind of guy. So the standard example is the 3-sphere, right? The first
3-sphere, the Berger 3-sphere.
Yeah, exactly. That's the 3-sphere. So what you're saying, well, I knew about the construction, but I didn't know what you're saying, that it is a geodesic sphere. So you said that the 3-sphere is a geodesic sphere in a symmetric space. Which one? I mean the Berger sphere. The
Berger sphere is the Berger sphere is a geodesic sphere of CPN.
CP, what n?
The complex projective space.
Yeah, but what n? What n? Which n? I mean the 3-sphere, the Berger 3-sphere, meaning that you take the standard Hopf-Berger over CP one, right? Over CP1? No, over CP2.
Yes.
Over CP2, sorry. Is the standard? No, I'm kind of confused. It's over CP1. Okay, so the 3, since I'm kind of like struggling with the first non-trivial example. So the base space is CP1, like the
sphere, but
right?
No, the example was in X7 in the quaternionic X7.
No, I'm talking about Berger, the standard, not your example. Just
no. I go before. Here is RP2 in X7.
I'm going much back. I'm sorry for my ignorance. I'm going to the not your example, but Berger example.
Yes.
Okay, just starting from scratch. Sorry, but it will be quick. I promise. Okay, so Berger considered the 3-sphere over the 2-sphere, right?
Yes.
With the fibers of circles.
Yes.
And now throw in a tau. You say less than 4/3, right? Yeah, you shrink or expand the fibers by a factor of tau, right?
Yes.
And you get another metric on the 3-sphere.
Yes.
Now you're saying, if I understand you correctly, that this sphere, so this I call the original Berger sphere, right? I don't know which tau he sent, but you said this one is a geodesic sphere inside a bigger manifold. It's like
yes.
Am I right?
In CP2 for some radius.
Okay, in CP2, all right. Now that's
it's not the quotient.
Probably. So it's a CP2. It's like U3 mod something, the mod U2 or something like that.
Yes. So and
then the U2 will be a symmetry group of this Berger sphere. That's what you're saying.
Yes.
Okay. So you just generalize it. You say this will be correct also for the quaternionic and octonionic.
Yeah. This is were calculated by Siller in some papers, so probably are not explicitly, but or some part of the folklore. So if you can do this calculation explicitly, and it's not difficult to see that in any case you get so changing the radius of the geodesic sphere, you get all. Of course, you can pass to the compact and then non-compact. You need the non-compact case also.
Okay.
Forget
So
all
understand.
Hopf-Berger spheres. But for the Berger sphere, usually with tau less than 1 is a geodesic sphere in CP2.
I see now that Alberto is answering. But only directly to me. Okay, but okay, so I understand. Okay, that's I think I understand. So your case is your first new case is the 7th sphere, right? The quaternionic, the first quaternionic case that you're considering is the 7th sphere. You throw in the tau, so
yes.
you are shrinking or expanding these 3 spheres inside the 7th sphere.
Yes, by some tau, and then this is a geodesic sphere in the quaternionic projective space.
Exactly, the CP, I mean HP2, I guess, no? Right, okay, that's
okay.
all.
So
now,
let's continue. Yes, I did not say in the introduction that this phenomenon appears when the geodesic sphere, to have a totally geodesic submanifolds in the geodesic sphere, which are not standard. Standard are intersection of the totally geodesic of the ambient space containing the center. This only appears when the geodesic sphere is not anymore convex. So the geodesic sphere, the geodesic ball, excuse me. When the geodesic ball is not anymore convex, then it appears those strange or those surprising examples. So general fact. Let us recall the intersection of geodesic sphere of a Riemannian manifold that contain the center is totally geodesic. So this is what I said before. This is a very general fact. A totally geodesic submanifold of a Hopf-Berger sphere is called well-positioned if the tangent space splits as the direct sum of some part which is horizontal, that is to say perpendicular to the fibers, and some other part which is tangent to the fibers. This is what we call well-positioned. So these are the notation, the horizontal and vertical distributions. Okay, let now be a vector which is either horizontal or vertical vector. Then, so some computation, not very difficult, shows that the Jacobi operator of the Hopf-Berger sphere lives invariant both horizontal and vertical subspaces. So the Jacobi operator lives invariant horizontal and vertical subspaces. Moreover, any horizontal eigenvalue is different from a vertical one. What does it mean? It means that a totally geodesic submanifold that contains V is invariant under the Jacobi operator, the tangent space, and so the tangent space of such a totally geodesic submanifold splits. So the conclusion is that a totally geodesic submanifold that the tangent contains a horizontal or vertical vector is well positioned. This always happens when the totally geodesic submanifold has dimension greater than the codimension of the fiber, because in this way there would be always a vertical vector. For example, in the usual Berger sphere, a totally geodesic of the just the opposite. So a totally, I don't say it properly. The main feature. If I have it, suppose in the classical Berger sphere, I have a totally geodesic submanifold of dimension at least 2. So since the fiber had dimension 1, so a totally geodesic of dimension at least 2 has in the tangent space intersect the horizontal subspace. So this implies that it has a horizontal vector, and having a horizontal vector, it's well positioned. So in any classical Berger sphere, any totally geodesic submanifold, of course, different from a geodesic, different from a geodesic, has a horizontal vector, and so by what we said before, is well positioned. And this always happens when the dimension of sigma is greater or equal than the dimension of the field, or dimension of the fiber plus 1. So let sigma be a totally geodesic submanifold of a Hopf-Berger sphere. If sigma is well positioned at some point, this is always another proposition. If a totally geodesic submanifold is well positioned at some point, then it is well positioned at every point. So it's rather standard to prove this. So if at some point is well positioned, it's always well positioned, and if at some point contains a horizontal or vertical vector, the tangent to the totally geodesic is well positioned. So now we have the following result. We have the following result: sigma totally geodesic submanifold of a Hopf-Berger sphere of factor tau, of course not the round sphere, and let M bar be the rank 1 symmetric space, such that this Hopf-Berger sphere arises as a geodesic sphere. So the following statements are equivalent. We almost have done it. Sigma is well positioned. Sigma is well positioned. The second is has a vertical horizontal vector. This is what we commented before. The tangent space is invariant under the shape operator of the shape operator. This is another of the shape operator of the geodesic sphere. And the other one is sigma is the intersection. So any well-positioned totally geodesic submanifold intersection of a totally geodesic submanifold of the ambient space. And so that means that a totally geodesic submanifold. So this equivalence, the equivalence number 4 would be that the totally geodesic submanifold is a standard in what we said before. Is the intersection of a totally geodesic of the ambient space. So this clear in some way deals with the standard totally geodesic submanifolds, and we have a lot of criterion to prove when a totally geodesic submanifold is a standard. So here in this table there are the standard totally geodesic submanifolds in the complex case. So that also appears. So there are spheres in any case, and in the other cases, so. In general, there are, excuse me, in general, a Hopf-Berger, so if you intersect a geodesic sphere with a totally geodesic submanifold of the ambient space, let us think linearly, so if you took normal coordinates, then the intersection is the intersection, like in the sphere, intersection of the subspace with the sphere. And then this is again a Hopf-Berger sphere of less dimension. Perhaps could be a round sphere. So this is the table. So observe that a totally geodesic manifold of dimension at least 2, we said it before, of a Berger sphere is well positioned since the dimension of sigma is greater or equal than the dimension of the fiber plus 1, is what we said before. And so are always well positioned. A totally geodesic well positioned as a manifold of a Hopf-Berger sphere is what I said before, a Hopf-Berger sphere, because it is a geodesic sphere intersected with a totally geodesic submanifold is a geodesic sphere in the totally geodesic submanifold. It's very, could be a round sphere in this case, because we call Hopf-Berger sphere when tau is different from 1. And so, and then well positioned, so this, it's better to see that than the explicit table, because so totally geodesic well positioned submanifold of a Hopf-Berger sphere are either Hopf-Berger spheres or round spheres. So now we get to a very general geometric facts that are that could be useful in a more general setting. So there are observations that that come all together in order to give some conclusions in our cases. So the first, the isotropy representation of the tangent space of the Hopf-Berger sphere, the isotropy representation. So we present here we call G, the G would be the K here. G would be K that acts transitively on the geodesic sphere. So the isotropy representation in the tangent space is polar. This is well known. Moreover, if we choose a vector which has a horizontal and a vertical component, which are both non-null, so we will choose a tangent vector to the Hopf-Berger sphere. So one part horizontal and one part vertical. Then when the principal orbit of the isotropy are a product of spheres. O sea, the principal orbit of the isotropy representation is a product of spheres. This only the representation. So the action of H in the whole Berger sphere is not polar. And the set of fixed vectors of the principal orbit of the principal isotropy is three-dimensional. So the set of fixed vectors is three-dimensional, and this the fixed vector contains V1, V2, the normal space of principal orbit is fixed, and then it contains also a horizontal direction. So in that way, one construct because fixed points of isometries correspond to a totally geodesic submanifold. In this way, this would be important totally geodesic three-dimensional submanifold. Any geodesic of a Hopf-Berger sphere is contained in a totally geodesic Berger sphere of dimension 3. Because of that, because I choose a geodesic. I choose a geodesic. Suppose digamos, both components of the tangent of the velocity are the horizontal and the vertical part are different from 0, and then the orbit of the isotropy of this is a product of spheres. The normal space is V1 and spanned by V1 and V2, and then we have another horizontal direction. So since the action is polar, we can so we can put this vector as a normal in the normal space, and then in that way we construct we put this geodesic. So we find directly the totally geodesic three-dimensional submanifolds are the fixed set of the isotropy of V. Let us continue. A totally geodesic local submanifold. This is general fact. It's very standard. A totally geodesic local submanifold of a homogeneous Riemannian manifold extend to an immersed complete totally geodesic submanifold. And this is intrinsically homogeneous. So a local homogeneous submanifold extends to a global one, but immersed. Could be. So another interesting fact is that a complete totally geodesic immersed submanifold of dimension at least 2 of a compact homogeneous geo space is either compact. So because a complete totally geodesic manifold of a compact manifold need not to be compact, because if you choose a geodesic which is not closed, then this is you get in this way that need not to be compact. But in general, what we prove is that in a compact homogeneous geo space, so a totally geodesic submanifold is either compact, or compact. So it's an immersed submanifold, but compact so means so it means that we have to go to a covering and then probably factorize after a compatible immersion. So it's either compact or sigma has a two-dimensional flat and totally geodesic submanifold. So we have to point out here that so if you go to the universal cover probably is not any more compact, but then you can factorize through a compact immersed submanifold. So, for example, in a closed geodesic, you get this example. But this is essentially so is a totally geodesic submanifold is compact, or there is a two-dimensional flat and totally geodesic submanifold in the ambient space. No Hopf-Berger sphere admits a flat totally geodesic. So this is interesting, you know, to include with this property. Also, one can prove that Hopf-Berger spheres admit no flat totally geodesic submanifolds of dimension at least 2. And the reason is that flat manifold using the isotropy you can always put as a normal space of the isotropy action, and then after that this would be totally geodesic in a Berger 3 sphere, but this cannot be. So the important point here is that any complete totally geodesic submanifold of a Hopf-Berger sphere is compact. This is important. This will be important then. We call the slope of a vector tangent to the Hopf-Berger sphere the quotient between the lengths of the vertical and horizontal parts. So the isotropy acts transitively on the set of unit vectors with the same slope, because the isotropy action, the principal orbit of the isotropy actions are product of spheres. This is because of that. Since any Hopf-Berger sphere is a geodesic orbit space, we have that the slope of the velocity of the geodesic does not depend on the parameter. So the slope is independent of the parameter because the geodesic is homogeneous. And another remark is that not remark, that we have to prove that to do some calculations. The set of slopes of closed geodesic is countable. So the slopes of closed geodesic is countable. Of course, we are yes, in any case, also is countable. So since any geodesic is contained by an element of a group in a three-dimensional Hopf-Berger sphere, then in order to prove this, it's sufficient to prove it in the Berger 3 sphere. Now, well-positional total geodesic are understood because they are intersection of the total geodesic of the ambient space, which are classified, and we can have a table of that. So the interesting question is to deal with non-well-positioned total geodesics and manifold. That total geodesics and manifold that do not arise in particular as a fixed set of groups of isometries. We regard the Hopf-Berger sphere as a geodesic sphere. So again, we say the same, of a rank 1 symmetric space of no constant curvature. And the injectivity radio is just, in the compact case, is P/2. P/2 because the maximum curvature is 4, no? Is P/2, or infinity in the non-compact case, the injectivity radio. So we have rescaled everything that a geodesic of length p pi is a closed geodesic, because in a rank 1 symmetric space, every compact, every geodesic is closed. So the geodesic closed at the time of pi, and up to pi/2, we have the injectivity radio. As we have seen, any total geodesic and manifold of dimension at least 2 is well positioned. So we disregard the case, so the complex space, so the usual Berger spheres or anti-Berger spheres are disregarded because does not appear any interesting total geodesic and manifold. So the shape operator of the geodesic sphere leaves invariant the vertical and the horizontal subspace. So we computed this explicitly, and we get it has only 2 eigenvalues, one horizontal and one vertical. So they are explicit computations only for the shape operator. And what is important is that the eigenvalues are always different. And the shape operator is negative definite if and only if M bar is either non-compact. In the non-compact case, the shape operator is negative definite. It's definite, so it does not matter if it depends on the choice of the normal direction. But it's definite, defined in the non-compact, and in the compact case, it's definitely defined up to tau, up to t equals p/4. P/4. And that means this is just the point where P/4, where the geodesic spheres are not anymore the geodesic balls, no spheres, are not anymore convex. Because if you go to the proof of the convexity of small balls in Riemannian geometry, there appears the shape operator implicitly of the geodesic sphere, and what is important to prove that the small geodesic balls are convex is that the shape operator is always definitely negative for small t. So now sigma will be not well positioned at totally geodesic Hopf-Berger sphere. And we choose gamma s to be geodesic starting at P. So then the slope of gamma is different from 0 and infinity, because it's not well positioned. So the tangent, the velocity of the geodesic has both non-trivial vertical and horizontal components. So this is, and now assume that gamma is not a closed geodesic. Assume that gamma is not a closed geodesic. Since M is a geo space, the closure of gamma R is an orbit of with dimension at least 2 of a compact abelian Lie subgroup of E. That is the closure of the one parameter group that gives the geodesic. So since gamma is contained in a three-dimensional totally geodesic Berger sphere, so this is what we call with the double isotropy, the fixed set of the isotropy of a vector is three-dimensional, and then this geodesic, the closure of this sphere must be contained in sigma 3, this three-dimensional Berger sphere that contains the direction of the geodesic must contain the closure, because are closed. Sigma 3 is closed and BP is closed. That must contain this. But now, if sigma 3, so if sigma 3 is included in sigma, so the sigma in this totally geodesic submanifold where it has a geodesic inside, gamma is a geodesic inside sigma. So if sigma 3 is included in sigma, so sigma 3, this standard Berger 3 sphere contains a horizontal vector. And so if it contains this horizontal vector, sigma contains a horizontal vector, and then what we see before, sigma is well positioned. Then the intersection of sigma 3 contains BP, because it's the closure of the geodesic, and it must be so the intersection of sigma with this three-dimensional Berger sphere contains the closure of the geodesic, and so it must contain the intersection. This implies that the intersection of sigma with sigma 3 is two-dimensional. So our sigma, total geodesic, with this Berger sphere of dimension 3 is two-dimensional. But we can check directly that sigma 3 admits no totally geodesic surfaces. This because the classification we can, so it is a standard, because otherwise it is also well known if a homogeneous manifold has a totally geodesic hypersurface, it would be of constant curvature. So, so in this case, what we prove is very important is that all geodesics are closed. A non-trivial geodesic of a not well positioned. So if the totally geodesic manifold is well positioned, this is not true. So it's not well positioned. So any geodesic of sigma is closed. And so, moreover, so any two such geodesics have the same slope. So all are closest geodesic with. So this is very important. A totally geodesic non well positioned submanifold. All the geodesics are closed with the same slope. And then from that, it is not difficult to put. So because since the isotropy acts transitively on vectors of the same slope, then projecting killing fields to the totally geodesic submanifold, one gets. It's not hard to prove that intrinsically sigma is 2-point homogeneous, and hence rank 1 symmetric space. So one can also use the homogeneous space of if all geodesics are closed. If in a homogeneous space all geodesics are closed, this is then the space is rank 1 symmetric space, but this is a very strong result. But also we cannot use this directly because we do not know that are closed with the same length. Could be so. So the closest at some time, but should be the geodesics of all of the same length to apply that. But we apply this. We just projecting killing fields. We obtain it is 2-point homogeneous and hence rank 1. A corollary: a not well positioned totally geodesic submanifold of a Hopf-Berger sphere is intrinsically symmetric. This is the corollary. So this was a very, very strong fact that we have applied to our characterization. So from the proposition and corollary, and this corollary that intrinsically a not well positioned totally geodesic manifold is symmetric, rank 1 symmetric, one has the following, and we have to do some explicit calculation. A not well positioned totally geodesic manifold of a Hopf-Berger sphere, regarded as geodesic sphere, is isotropic with respect to the second fundamental form. What does it mean? That any vector in the tangent space, if if alpha is the second fundamental form, alpha BB is 0. So and this so if it's isotropic, and if any vector is isotropic, means that sigma is also totally geodesic in the ambient space, because the geodesics are the same. Because a geodesic inside a geodesic of sigma, since alpha of the geodesic is gamma, alpha gamma prime is 0, then this is also geodesic in the ambient space. And so this is very the crucial theorem for the classification. So in any case, totally geodesic manifolds are totally geodesic manifold of the ambient space. But now this totally geodesic manifold of the ambient space does not pass through the center of the sphere, of the geodesic sphere. So here we listed the totally geodesic submanifolds, and appears spheres and spheres which are so similar to the fiber, but are in somewhat not vertical. So there are some spheres that are situated in not well positioned, totally geodesic, but then other appear some projective spaces of dimension 2 and 3, depending on tau and depending on tau of the type of the Hopf fibration. So, for example, we have the appears for some in the quaternionic Hopf-Berger sphere. In the quaternionic Hopf-Berger sphere appear some spheres of the dimension. So, of course, dimension is dimension 7. So some spheres. Of dimension 7, that the full isometry group is not of course you have a totally geodesic 7 sphere, you have 6 spheres, 4 spheres, 5 spheres, or any, but what happens is that these are the homogeneous one. The homogeneous ones that are extrinsically homogeneous, but the others are intrinsically homogeneous but not extrinsically homogeneous, the other spheres. This is the congruence classes of the totally geodesic submanifolds. Also, let's say again, for example, in the 15th sphere, there are 7 spheres that are not well positioned, totally geodesic, but the group that acts transitively on it is not the full group of the 7th sphere. And this implies that some of the spheres are homogeneous and others are not anymore homogeneous, of less dimension. So, okay, we finish here the exposition. So.
Thank you very much. It's really interesting talk. Are there questions?
Hi, Carlos. This is Wolfgang.
Hi.
Hi, Carlos. This is Wolfgang.
Yeah.
I have a question. So one of the values that's special for you is tau is equal to 1/3. Is there any geometric meaning behind that value 1/3?
No. We have our calculations gave that for 1/3 appears so this phenomenon. We don't have a good geometric understanding of what is happening at 1/3. At 1/4, yes, the geodesic balls are not any more convex, and this has something to do. But up to now, we perform computations and appear these examples, but we have no that would be probably you could find a reason why this appear.
Value 1/3. That's whether for less than 1/3, the two-plane of maximum curvature is vertical, and for bigger than 1/3, it's horizontal.
Again, so I listen very softly.
For tau less than 1/3, the two-plane maximum section curvature is vertical, and for tau bigger than 1/3, it's horizontal. So it switches at tau at 1/3.
So at 1/3 switches the vertical.
The plane of maximal section curvature.
The maximal sectional curvature. So at 1/3, so the vertical is the same as the horizontal, some horizontal.
Correct.
Nice. I didn't know that. So you classify the sectional. You studied the sectional curvatures of those spaces and the.
When I compute the pinching and things like this, it's in one of the other papers.
So at 1/3, it happens this phenomenon. Nice, very nice.
That's in a paper with Ruja Badiani.
At 1/3.
Yes.
Nice. That would have something to do with that.
Could be, yes.
Yeah. Of course, the direct. So also in one pi over 4. Also, we know that, of course, being the geodesic, not anymore convex, the geodesic spheres, that then it could be some, how do you call, light vectors or isotropic vectors, and this implies that totally geodesic submanifold could be totally geodesic in the ambient space. But here, yeah, so have a very, very, very nice. Thank you very much, Wolfgang, for such
very nice talk. Very nice talk. Very strange submanifolds. I like it.
Yeah, very strange. We're very surprised. So we have to work a lot because there are a lot of geometric arguments, but also we have to deal with some computations that's not so nice in some way.
Thanks.
Are there any other questions or comments or? No, thank you again. That was really enjoyable.
Okay, thank you. So, thank you.